All right, our next convergent diagram is going to be continental and oceanic. So we're going to have the oceanic plate coming in from the left and the continental plate coming in from the right. So at first, this is going to look very similar to the diagram that we just drew that was the convergent oceanic to oceanic. We're going to start the same way, where right at the center of the page, we're going to start our ocean plate. Okay, and it's going to dive under the continental plate and be subducted. So we're going to go ahead and draw that out down here. And then round it off, making it the subducting plate, then coming back up. Now, when we have ocean to continental, it's always going to be the oceanic plate that subducts. The oceanic plate is always going to subduct under the continental plate because the oceanic plate is made of much, much denser material. It's that basaltic type lava that makes it dense enough that it's going to sink down into the mantle, while the continental plate is going to come out on top every time. Okay, so we'll fill in the rest of our oceanic plate here and then switch brushes to do the continental plate above it. Now remember, our continental plates are have a heart of granite. They'll never take you for granted. Shameless geology pun there. Granite is the main constituent of continental plates, but they are also covered in sedimentary rock layers as well. Now, most sedimentary layers form in specific situations, as many of them actually form on the ocean floor as limestones and other things. And we're going to talk about how they wind up getting on top of the continent here in a moment. All right, so we've got our ocean plate. We're going to put on our continental plate. It's going to start out just like our oceanic plate earlier did. It's going to rise up a little bit higher, of course, okay, and then it's going to form a mountain. We're going to have that mountain on top again, just kind of like the volcanic island arc. But this time, this volcano is caused by the melting ocean plate underneath it, rising up through the continental plate. All right, so we're just going to sketch that out right now. We'll come back and fill it in later. All right. Now, we talked about the sedimentary rocks on top of the continental plate. As the ocean plate goes underneath the continental plate actually scrapes off layers of sediment from the ocean floor. And it accumulates on top of the continental plate right there at the border. So we'll put some black layers kind of coming up onto here. And we call this feature an accretion wedge. Okay, so all this material is getting scraped off the ocean crust here and piling up on top of the continental plate right in front of this volcanic mountain that it's forming. All right, now just like before, we've got the uppermost section of the mantle that's right below these. That is made up of magma. And right below that's going to be the asthenosphere, of course, where all of this kind of rides on top of and the mantle convection is happening. Okay. So our oceanic plate's diving way down underneath. I'm going to extend it actually a little bit for this drawing. Okay, it's coming out here and it's melting and it's coming up again through the plate that's above it, through that continental plate. And again, the magma that is rising up through the continent here is silica rich because of the ocean water and those limestone sediments that have been brought down with the ocean crust. And it makes a very viscous, very dangerous type of lava that actually erupts in spectacular fashion. Okay, so I'm going to extend the ocean plate down just a little bit more so it's right under the mountain. Okay, and that lava is being melted and coming up through. Let's add more red. It's going to make it a dark lava so we can see the distinction between it. So we know it's got part of that old ocean crust in it. It's bubbling up. Now sometimes it comes up and it doesn't reach the surface. And it cools under the continent, inside the continent. Okay, because the continent's really thick, so it's going to take a long time for this magma to come up. So sometimes it doesn't make it all the way to the surface, doesn't actually erupt as a volcano. Instead, it kind of stops right inside the continent and forms a intrusive igneous rock. Okay, granite is one of the classic intrusive igneous rocks. It forms underground from magma that couldn't escape all the way to the surface. And it cools slowly, so granite is usually got very, very large crystals. It's a very, very pretty rock. That's why it's used as countertops and building materials. Okay, but that's an intrusive igneous rock, which happens there. Sometimes it does escape to the very top, and it makes some of the most explosive volcanoes. Mount St. Helens is a great example of this process. Explosive, very violent eruption, because as it comes up, that magma has trapped gas and air inside it, and as it comes up, it's like shaking up a Coke bottle and opening it. It lets all that pressure off, and it explodes in spectacular fashion. Okay, so we're going to come back again with our green and fill in the rest of the continental plate there. So the eruptions around the edge of the oceanic plates, where they subduct underneath the continental plates, these cause some of the most violent eruptions and the most violent earthquakes. This subducting of the oceanic plate underneath, there's a lot of friction there. And that friction causes the plate to grab and be pulled underneath. And as that happens, every now and then it stores up immense amounts of elastic potential energy. It's pulling down and then it pops up. And when it releases and pops up, that's when the strongest earthquakes occur. And they are called mega thrust earthquakes. Mega thrust earthquakes happen where oceanic crust is subducting underneath the continental crust. And it happens right along that section. What's amazing about those earthquakes is those are the ones that we can use to map out the interior of the Earth. So it's plate tectonics and seismology caused by plate tectonics that allows us to actually see inside the Earth and explain the actual process that's making those earthquakes. So without those earthquakes, without those seismometer readings, we wouldn't know what was inside the Earth. Okay, so I'm going to just kind of fill in around these intrusive magma bodies. Okay, now that magma is really hot, so as it comes up, it's actually melting through the continental crust above it. So sometimes continental crust gets included inside those magma chambers. And we call those very, very large clasts of rock included in with. talk about how to relatively date layers later in my class. And intrusive rocks are always younger than the rocks they cut through. Because what had to be there first is got to be younger. So these intrusive igneous rocks are recycled material. Right at the edges of those magma bodies, those magma plumes coming up through the continental crust, it's contacting that rock and incorporating it into itself, but also melting it. So we get contact metamorphism. Now remember your three rock types. You've got igneous, which is the lava rocks, sedimentary, which is made up of bits and pieces of other rocks, and then metamorphic, which is rocks change from heat and pressure. And it's contact with these very hot magma bodies that can actually alter the chemical structure of the rocks they come in contact with and make, whoops, got a little red there, and make metamorphic rocks. So metamorphic rocks are indications of very, very strong tectonic forces. Where we see magma come into contact with other rocks, or we see intense pressures causing those rocks to melt. So it's okay that we blend in these layers right around those magma bodies, because that's what happens. They melt and they become blended, and there's this gradual metamorphism that happens around them. Okay, so we've got all our colors, I think, filled in. Let's add the ocean over top the oceanic boundary, or oceanic plate. All right. Use the big brush to make this go quick. All right, so continental plate subducts underneath, or I'm sorry, the oceanic plate subducts underneath the continental plate here, making those deep trenches. We're going to want to label that on our diagram. Okay. The accretion wedge is something we also want to label. That's the accretion of material from the oceanic plate being scraped off and collecting on top of the continental plate. Okay, this winds up in places like the west coast of South America is an example of this plate boundary. The Andes Mountains are volcanic mountain ranges caused by a subducting ocean plate. The Pacific Ocean plate subducting underneath the South American plate. And on top of those mountains, on top of the Andes, is limestone that used to be on the ocean floor, but it's been scraped off and pushed up to the very top. So you can find ocean fossils on top of these mountains. That just shows how strong these plate tectonic features can be. Add a little waves. Add some waves. All right. So that finishes this diagram. We're going to label it. We need to add the convection current arrows again. Convection currents at subduction zones are in the mantle, in the asthenosphere. They're moving together here and then subducting down, following that subduction pattern. Okay, so that's where our arrows are going to go. Alright, so we've got the asthenosphere, which has got mantle convection happening. The very bottom of the lithosphere, which is actually the top part of the mantle. Ocean plate and continental plate coming together, getting all mixed up together. The ocean plate melting, rising up, causing these massive volcanic eruptions. Add some smoke to the volcano. These violent volcanic eruptions all the way around the Pacific Ocean. So we call it the Ring of Fire because of that. That ring of fire is from all those volcanoes all the way around the oceanic plates where they're subducting underneath the continental plate. Let's make this a little brighter. All right, so that finishes up the diagram. Make sure you get yours labeled. Make sure yours is labeled. All those features. Deep ocean trenches, subduction, the direction that the plates are moving. Of course, they're coming together here. And that finishes up our diagram of an oceanic to continental collision. Next, we'll do a continental to continental collision.